Pluto is a distant, mysterious, and relatively small planet that was once classified as a member of our solar system's planetary lineup. However, in recent times, renowned astrophysicists Neil deGrasse Tyson and Michio Kaku have reintroduced Pluto into the public conversation with a surprising revelation. They suggest that this icy world might be on a collision course with Neptune. This raises intriguing questions. How could this occur, and what would the consequences be for such a massive event? Could this be an extraordinary cosmic anomaly, or is there a deeper cause behind the potential catastrophic impact? Join us as we delve into the possible results of a Pluto-Neptune collision. Pluto, formerly considered the ninth planet, was demoted to a dwarf planet due to its unconventional orbit. Still, it remains a focal point for astronomers and researchers in the scientific community. Recently, leading scientists have proposed that Pluto's orbit is dangerously close to Neptune's, sparking concerns about a potential crash between the two planets, which could ultimately present a significant threat to Earth. How could something like this even happen? The journey of Pluto around the Sun is unique among all the other planets in our solar system. It takes a staggering 2048 years to complete just one orbit, and since its discovery in 1930, it has not yet finished a full revolution. Yet, interest in Pluto persists due to more than just its lengthy orbit. It also follows a highly elliptical, or oval-shaped, path that deviates sharply from the nearly circular orbits of other planets. What makes Pluto's orbit even more peculiar is its inclination, at an angle of 17 degrees to the ecliptic plane. This steep tilt contrasts with the relatively flat orbits of most other planets, and when combined with the elliptical shape, adds layers of complexity to its orbit. One of the most fascinating characteristics of Pluto's path is its intersection with Neptune's trajectory. For about 20 years in every orbit, Pluto actually passes closer to the Sun than Neptune does, which seems to contradict their expected positions in the solar system. This raises the natural question: why hasn't Pluto crashed into Neptune, given their crossing orbits? The answer lies in the gravitational influence of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers were puzzled by its strange path, unlike other planets that lie close to the ecliptic plane. Pluto's orbit, with its steep tilt and elliptical shape, was a mystery for scientists to unravel. Further investigation revealed that Pluto's orbit does, indeed, intersect with Neptune's, raising concerns about potential instability. However, the stability of Pluto's orbit, despite these complexities, highlights the intricacies of celestial mechanics. The three-body problem in astrophysics involves predicting the motion of three objects in space, like Pluto, Neptune, and the Sun, and understanding how their gravitational forces influence one another. It's like trying to forecast the movement of three interconnected bodies based on their starting points and the forces they exert on each other. In Pluto's case, this problem illustrates how its orbit, along with Neptune's and the Sun's gravity, work together in a complicated but stable manner. Two important concepts, acyl libration and scope libration, along with VZK oscillation, are key to understanding this phenomenon. According to astrophysicists, acyl libration helps keep planets in their orbits, and when Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune, creating a buffer that prevents the two orbits from colliding. Scope libration, on the other hand, refers to Pluto's vertical movement in its orbit. When Pluto comes near Neptune or any large planet, it is positioned above their orbital plane, providing an additional safeguard against a potential crash. Another crucial factor in maintaining Pluto's orbit is the VZK oscillation, named after researchers V, Z, and K, who studied the gravitational interactions between objects in space. This oscillation helps explain why Pluto's path remains smooth despite its seemingly erratic orbit. In essence, even though Pluto's orbit appears chaotic, the VZK oscillation ensures it maintains a steady course over long timescales. All of these factors work together to stabilize Pluto's path, preventing it from crashing into Neptune or drifting off course. The three-body problem is essential for understanding how these orbits evolve over time, demonstrating the powerful and predictable forces at play in space. In the late 1980s, computer simulations showed that despite these stabilizing factors, Pluto's orbit is still somewhat unstable, with minor variations that can cause noticeable shifts over thousands of years. Nevertheless, Pluto's orbit has proven to be surprisingly stable over extremely long periods, keeping this turbulence under control. Further computer simulations have revealed the influence of larger planets like Neptune, Jupiter, and Saturn on Pluto's orbit. Interestingly, Pluto's orbit shares a unique relationship with Neptune's. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This synchronized relationship helps maintain the stability of Pluto's path. However, Neptune isn't the only factor at play. Jupiter's gravity also plays a significant role in ensuring Pluto's orbit remains steady, and Saturn's gravitational influence is important as well. These simulations show that Jupiter's gravitational pull alone is powerful enough to keep Pluto's orbit stable for millions of years. Together, Neptune, Jupiter, and Saturn seem to be working in harmony to ensure Pluto follows a safe and steady path. These mechanisms are essential in preserving order within the solar system. Without them, the solar system could be far more chaotic, with bodies like Pluto potentially colliding with others or even being ejected from their orbits, triggering a cascade of events. For Pluto, understanding its orbital mechanics is crucial to grasping the solar system's broader dynamics. This case highlights how even the most seemingly erratic orbits can reach a state of balance through the complex interplay of gravitational forces and orbital mechanics. It also underscores the importance of continuous observation and investigation to better understand our place in the cosmos. As we explore the depths of space, we inevitably confront the mysterious nature of celestial bodies, and Pluto's peculiar orbit serves as a prime example of the unpredictability inherent in the universe. The concept of orbital chaos, which refers to how small changes in an object's orbit can lead to drastic long-term effects, is vividly illustrated in Pluto's case. Even slight variations in Pluto's position or velocity can dramatically alter its long-term trajectory. Computer simulations have been incredibly helpful for scientists in understanding how Pluto moves through space. By adjusting small variables, astronomers can predict how these changes will affect Pluto's orbit over time. In the late 1980s, simulations revealed that even though Pluto's orbit is kept in check by mechanisms like acyl libration and scope libration, its path can still be unpredictable, especially over extended periods. A small shift in Pluto's position or velocity could result in a radically different orbit, though the stability remains over billions of years. This shows that Pluto's orbit, while chaotic, maintains a certain order when observed on vast timescales. Predicting celestial events, especially those involving erratic orbits like Pluto's, present significant challenges. The inherent unpredictability of these systems makes long-term predictions fraught with uncertainty. Although mathematical models offer powerful tools to help us understand and forecast the movements of celestial bodies, they are limited by the accuracy of the initial conditions. Even tiny errors can lead to vastly different outcomes, making precise predictions difficult. The chaotic nature of planetary orbits, like Pluto's, reminds us of the ever-changing and dynamic nature of the universe. While we've made impressive strides in space exploration and understanding, Pluto's orbit highlights how much remains to be discovered. Understanding the gravitational effects of larger planets on Pluto's orbit provides valuable insight into the overall dynamics of our solar system. It demonstrates how the location and gravity of each planet can have far-reaching impacts on the stability and direction of other bodies within the system. So, why are major astrophysicists just now raising alarms about the potential for a collision between Pluto and Neptune? Despite all the forces at play that seem to prevent such an event, scientists like Neil deGrasse Tyson, a key figure in popularizing cosmology, bring new perspectives to these mysteries. Tyson, known for his role in Pluto's reclassification as a dwarf planet, offers insightful analysis on the evolving understanding of celestial mechanics and the public's fascination with exploring the unknowns of space. Tyson's view on Pluto's renaming is not one of downgrading but rather an essential adjustment as our knowledge of the solar system continues to expand. He sees the complexities of orbits like Pluto's as indicative of how much more there is to learn about space. However, despite Tyson's optimism about continuous discovery, he remains cautious when it comes to predicting the fate of Pluto. He acknowledges the possibility of a collision between Pluto and Neptune, which would result from gravitational forces too great to ignore. Yet, despite the chaos in Pluto's orbit, Tyson and other astrophysicists note that such a collision remains highly unlikely in the near future. The vast timescales involved, spanning millions and even billions of years, make it impossible to predict Pluto's eventual fate with certainty. Even though the notion of a future Pluto-Neptune crash captures the imagination, the reality is that numerous factors contribute to the stability of Pluto's orbit. Gravitational forces from distant objects, like Jupiter and Saturn, as well as smaller bodies like asteroids and comets, create a web of stability that has kept Pluto's orbit largely predictable over millennia. Nevertheless, this does not rule out the possibility of unforeseen changes in the future. As our understanding of the solar system continues to evolve with new discoveries, the dynamics governing Pluto's orbit could change. An intriguing aspect of this ongoing discussion is the role of the Kuiper Belt, the vast region beyond Neptune filled with icy bodies. Pluto is just one of many dwarf planets in this distant region, and many objects in the Kuiper Belt share similar orbital characteristics. The interactions within this region could offer new insights into Pluto's future trajectory and its relationship with Neptune. As scientists continue to study the Kuiper Belt, they may uncover further details that shed light on the gravitational interactions affecting Pluto's orbit. Additionally, the prospect of a Pluto-Neptune collision raises broader questions about the behavior of celestial bodies over time. What happens when objects in the solar system interact over vast periods? Could such an event spark a chain reaction affecting the entire solar system? One theory is that a Pluto-Neptune collision could have catastrophic consequences. The resulting energy could send shockwaves throughout the solar system, disrupting the orbits of other bodies, and potentially even impacting Earth. The explosion of energy could also lead to the displacement of objects or even result in new celestial bodies entering the solar system. While such an event is improbable in the near future, it serves as a reminder of the unpredictable nature of space. As we continue to study Pluto's orbit and the forces shaping our solar system, we are reminded of how little we still understand about the universe. Every new discovery about Pluto, Neptune, and the outer reaches of our solar system adds to our understanding of the cosmos. For now, the potential collision between Pluto and Neptune remains a topic of scientific inquiry, but it provides a fascinating glimpse into the powerful forces at work in the universe. In conclusion, while the possibility of Pluto crashing into Neptune makes for an exciting topic in astrophysics, the likelihood of such an event happening anytime soon is slim. The mechanisms stabilizing Pluto's orbit are strong, and it is far more probable that Pluto will continue its orbit around the Sun for millions of years. However, research into Pluto's orbit is ongoing, and as we learn more about the forces at play in the solar system, our predictions about the fate of this distant world may evolve. Until then, the mystery surrounding Pluto and its connection with Neptune continues to captivate scientists and skywatchers alike, offering a unique glimpse into the far reaches of our cosmic neighborhood. As we delve deeper into the intricacies of Pluto's orbit, it becomes clear that understanding the long-term stability of such distant bodies is not a simple task. The study of Pluto's orbit highlights the complex nature of our solar system's dynamics. While predictions about Pluto's path are influenced by various gravitational interactions, there remains a level of uncertainty. The potential for a Pluto-Neptune collision, though unlikely, captures the imagination of scientists and the public alike, offering a glimpse into the chaotic and unpredictable nature of the universe. The relationship between Pluto and Neptune, with their shared orbital resonance, has fascinated astronomers for decades. The fact that Pluto and Neptune's orbits are so intricately linked, Pluto completing 2 orbits for every 3 completed by Neptune, adds another layer of intrigue to their cosmic dance. This resonance helps prevent a collision by ensuring that the two bodies are always separated by significant distances. However, as Pluto continues to orbit the Sun in its eccentric, tilted path, it will still encounter moments when it crosses into Neptune's orbital zone. The question remains: can this delicate balance persist indefinitely, or is there a point at which external factors, such as the perturbations of other planets, could disrupt this equilibrium? Additionally, one must consider the broader picture of the solar system. While Pluto's potential collision with Neptune might seem like a dramatic event, it would not occur in isolation. Such a collision could have far-reaching consequences for other objects in the solar system, especially those in the Kuiper Belt and beyond. The Kuiper Belt, home to countless icy bodies, is a vast region that stretches far beyond Neptune's orbit. Objects within the belt are thought to be remnants from the early solar system, and understanding their behavior could help scientists predict the long-term fate of Pluto and similar bodies. Interestingly, many objects in the Kuiper Belt have highly elliptical orbits that overlap with Neptune's. This presents another layer of complexity in the study of orbital mechanics. While these objects don't collide with Neptune or Pluto directly, the gravitational interactions between them are still significant. The presence of these objects can affect the orbits of other bodies, including Pluto. As new discoveries continue to emerge in the Kuiper Belt, researchers may gain fresh insights into the gravitational forces that shape the movement of Pluto and its neighbors. For example, studying the orbits of these objects could provide a clearer picture of how Pluto's trajectory could evolve over millions of years, potentially shedding light on its future interactions with Neptune. Despite the numerous factors that help stabilize Pluto's orbit, scientists remain cautious in predicting its long-term path. The dynamics of the solar system are not static. They are subject to constant change. Even slight variations in the positions or velocities of the major planets can lead to significant alterations in the orbits of smaller bodies. The fact that Pluto's orbit is both irregular and influenced by the gravitational forces of distant planets makes it inherently unstable over very long periods. This makes long-term predictions about Pluto's future trajectory a challenging task. In addition to the Kuiper belt, another factor to consider is the potential influence of objects beyond our solar system. The solar system is not an isolated system. It exists within the larger galaxy, and the gravitational forces of nearby stars and interstellar objects can, in theory, affect the orbits of bodies like Pluto. These external forces are difficult to predict, but they could alter the stability of Pluto's orbit in ways we don't yet fully understand. As our knowledge of exoplanets and distant stellar systems grows, it's possible that we'll discover new influences on the solar system that could affect Pluto's path. Moreover, the long-term stability of Pluto's orbit is further complicated by the fact that the solar system itself is in constant motion. The Sun and all the planets, including Pluto, are not stationary but are instead orbiting the center of the Milky Way galaxy. Over billions of years, the gravitational interactions between the Sun, planets, and other stars can lead to shifts in the positions of celestial bodies. While these changes occur on timescales far longer than human history, they can ultimately affect the stability of objects like Pluto.